idea of some of these, like this book? Okay. Some of the applications and stuff that this is used for, but before we go into that, actually, to give you an idea of how deep the rabbit hole goes with this kind of stuff, trail of thought experiment with me, if you will. Okay. Imagine you wake up one day and suddenly you're an amoeba. Okay. Just wait for it. Follow it around. Okay. But you're a strange amoeba that has all the senses and sensory processing abilities of a human. Okay. You have no knowledge, you have no background, you have no experience, but you have all of that equipment built into you. Well, how would you start learning about the world? Okay. Things would start interacting with you. And over the course of time, those interactions would generate chemical signals in your body, your blob, that would start making patterns stronger. So you'd have things like, okay, this gives me pleasure, so I move towards this. This gives me pain, so I move away from that. And eventually, that would start stacking up. Now, imagine this goes on for billions of years. And you multiply, you evolve, you start changing your body's shape. You start being able to do these analyses more and more easily. And you've been doing it so long that you've completely forgotten where you started. So now once you become a human, basically, at this point, where you've got a fully evolved set of knowledge and brain, the question becomes, let's say you encountered that creature that you started out as today. How would you teach that everything you know? This is where machine learning comes into play. Machine learning is a subcategory of artificial intelligence. Essentially, it's sort of the most basic foundational learning for things that will start doing intelligent design, intelligent systems, etc. So I'll leave that at that, but then we'll just go into some of the applications that they talk about here. Oh, sorry. Keep forgetting about the camera, my bad. No, mute. Thank you. Okay. So these are some of the ones that most people are familiar with right off the bat. Okay. You probably have heard of things called predictive modeling and computerized statistics. Those fields actually overlap machine learning. The biggest difference in the two cases is that those are just a standard predictive algorithm, where machine learning is designed in such a way that it takes that information and tries to go one step further. It tries to figure stuff out on its own. So like up here, you've got optical character recognition. Well, we all agree to a certain basic set of symbols we use for numbers, but every time one of us writes it, it looks different. Okay, and that amoeba I was talking about, how do you teach it that those are all the same thing? This thing, predictive policing, this section over here is sort of the NSA sort of stuff, the big brother set of things, facial recognition. They track people through airports under security when there's a security threat. And if you really want to see how this thing is modeled in a much stronger way, go look at England, especially after the Olympics came through in London. Cameras everywhere. I mean, really, if you're anywhere in England, you're being watched. It's just that simple. Okay, unless you're in a little box, maybe. So like predictive policing up here, surveillance systems. It's all the same kind of stuff. I almost guarantee you somewhere that there was a machine out there that guaranteed that predicted Trump winning last year. I can almost guarantee it. But then you get down to some of these more simplistic lifestyle, life pleasure kind of things like Netflix and SoundCloud. If you ever look, okay, so you tell them I like these 12 movies. Well, they can't really predict too much with that if that's all they've got. But when you get 100,000 people, 1 million people, maybe up to the billions. I know Facebook's over 1 billion, but I don't know about Netflix. So actually, I think Facebook's at like 2.3, something like that. Anyway, and they do it too. So what you start doing is people talk about big data. You've got all of this data about what's going on. You start pulling it out, and you start extracting it, you start processing it, you start breaking it down. And you use that to teach the computer, hey, when this person likes this, okay, this person likes sci-fi, doesn't like anything else. Okay, they'll probably like this sci-fi movie, but they're not going to like this rom-com. So you pile up your suggestion. Stuff like Amazon, same kind of thing, except you're selling things as opposed to just displaying a movie. Yeah, of course, everybody I think is familiar with personal assistants here. I love the Clip It diagram. If anybody didn't know, that little thing you show up on Microsoft Office was actually called Clip It. So they got Google now, Cortana, Apple, Siri, etc. Every little time you say something into your phone, everything you said gets recorded and translated into a database. That information is then used to be able to break down sound phonemes in other people, so they can try to actually do a statistical model and create a pattern, so that when somebody, you think about it, there's the rate I speak at, and the volume and pitch and all the variation in it. He doesn't sound anything like me unless he's getting really loud for some reason. But both of us can pick up Siri, Cortana, or Google's the Google search and say, okay, Google, do this, and it understands it. This is the one that I'm honestly not that fond of. The self-driving cars. I don't like that. I honestly don't like the idea of a car that could suddenly take off without me wanting it to or something. But anyway, because I mostly don't trust systems like that. Okay, so like I said, that's basically where the rabbit hole takes you. You're basically taking all this data, feeding it down, and figuring things out. And how the life cycle and stuff goes is going to be talk to you about Ben.
Okay.
Enjoy.
So, machine learning is like any other problem in engineering. We've got a tool, we've got some specifications, a data set to work with, and we're looking for some results. So a machine learning software gets trained starting with a data set. It could be anything. It could be like an Excel spreadsheet of data with lots of records and stuff. It could be a set of photographs, perhaps of birds or something. You're trying to identify a bunch of photographs of a bird. Whatever it is, you start out with a set of data that you're trying to identify something about using this algorithm. And then you start out by creating kind of a reward mechanism. You tell it what you want to find inside this data. Maybe it's that bird in that photograph. You want to identify birds inside photographs. I don't know, that's a stupid example. So you tell it what you're looking for. You give it a system to judge how close it is, whether that's feeding it in whether the photograph actually had a bird in it or not, or something to that effect. And then it just kind of sits there and crunches on it and comes up with a model that it figures, this basically describes the data. And so then you take some more data and you figure out whether it's capable of predicting on that new data. Probably isn't if this is your first go around, so you try again and you continue to just do this process over and over again until your algorithm is capable of identifying whatever it is you want to do. One of my favorite examples at the moment was something that happened about 2 years ago now, I think. How many of you guys have heard of AlphaGo? Show of hands. A couple of hands around there. Okay, so about 2 years ago, there was a big deal where this machine learning algorithm beat the world champion Go player. If you've ever seen Go, it's kind of like really, really complicated chess. It's a 19 by 19 board. There's more possible move combinations than there literally are atoms in the universe. You can't brute force a problem like that. So most computer experts thought it would be 10, 15 years in the future before we could finally beat champions with a program similar to that we did with chess. But this machine learning program started out by looking through this database of Go games that have been played by masters in the past. But then they went further. They actually pitted it against itself. It was continually playing games against itself, improving its knowledge over and over again, year by year, until 2 years ago, it was actually able to beat the world grandmaster. There's an interesting set of YouTube videos if you're into Go, I guess. But data for this process can come from anywhere, even from playing itself. The main problem is to just develop an algorithm that can use that data usefully. So that leads me to Victoria.
So we're not going to, by the end of the day, be ready to program an algorithm to play Go. We are going to start in this club from ground zero. You don't need any prior experience in programming, data analysis, computer science, anything. The goal of this club, HECML, is to take all of us from whatever skill level you are and to make you capable of implementing machine learning or of working intelligently with machine learning systems and whatever industry you're going into. So if you're in engineering, I think a lot of us are in engineering. Raise your hand if you're not an engineering student or person. Okay, cool.
We need to branch out our advertising.
Yeah. How many mechanical people do we have? Awesome. Nice. Yeah. So this may seem like an electrical domain because of the programming and the data analysis, but this is becoming more and more relevant to all sorts of engineers. This sort of iterative learning and predictive modeling can be applied to mechanical systems as well. can also be used to take problems that are very complicated and the equations describing them would be very difficult to model explicitly. Instead, you can give a simpler problem to a machine learning algorithm or a neural network. So what we're going to do in this club is today we're going to explain the basics of ML. The next couple of weeks, we're going to take you through a crash course in Python. And we're not going to teach you everything. You're not going to be a master software engineer, but you'll have basic Python competency. You'll know how to find information when you need it, how to write basic functions, and how to take functions and libraries that are already developed and use them in a certain situation. So to be able to do that, we also need to know some basic computer architecture, because when we start working on computationally intensive projects, you're not just working on your laptop, you're maybe working on a specialized computer or systems of computers. So we need to know a little bit about computer science. We also need to know a little bit about statistics to be able to see how well our algorithms are doing. All of these things we're going to introduce to you and give you the basic skills so that you'll have some familiarity with them. If you want to take it a step further and be able to apply these techniques, we recommend doing the homework assignments that we'll be delivering along with the lectures. So after we go through our crash course in Python, we're going to be spending each lecture focusing on an algorithm or a program that solves a specific problem. We're going to demonstrate it and explain how it works, and then we'll send you home with something similar. And in the week between, you can try and program on your own. And when you come back the next week, we'll have time at the end of meetings to ask questions and break it down from there. So that's the basic layout of how this club will go. Do you have any questions about the curriculum of the club or kind of what we're covering here? Or about what you need to come to this? Okay, cool. So I'm going to show you all a couple of examples of machine learning algorithms. And I'm going to show you some very basic ones because I'm just going to run it on this little laptop here. So the first one I'm going to show you is, what is it called? Plot species distribution, I think. The plot species distribution model. So I'm going to call the Python interpreter, and then I'm going to tell it to run this little script. Species distribution. Okay, and it's going to...
You've got a CD before you can run Python.
Wasn't I in the...
Python was...
Yeah, you misspelled Python.
Okay, so it's going to take it a minute to compute this, because this is actually a little bit of an intensive task for my little laptop. What it's going to do is we're going to see... Oh, awesome. I'm running fast today.
Right past
So these little black dots are where some sloths are.
Slots. That's the smiling slots, the platypus.
Platypus. So yeah, so we've got some sloths were found in these locations, and biologists are wondering where can we try to find some more instances of these sloths. Where would we see them? And the problem is we don't have a lot of information about where they do exist. So we don't just feed into this algorithm the instances where we've seen the sloths. We fed in 15 other factors, geographical factors, environmental factors, and variables. And so you can see that the prediction that is made is not just affected by, I don't know if y'all can see in the back the little black dots. The little black dots are just right here. But we see sort of a high probability of finding another sloth down here because it's calculating intuitively the kind of environment that a sloth likes and predicting based on that. So we're able to predict based on a lot more factors. And this is probably like the Sahara Desert over here. What's your question?
As you become more aware, is it also just simple as plugging in the next factor? So you can create a more complicated algorithm just by inserting, okay, now let's start testing for this.
Yeah, so if we only had 2 parameters and we want to add another parameter to make our model more robust, absolutely. But there's a problem there called the curse of dimensionality. The curse of dimensionality is that the more dimensions so we can think of this as a multidimensional graph, and every time you add a new characteristic, you're adding a new dimension to your graph.
You're adding a new axis.
You're adding a new axis. And so it increases a lot the amount of data that would be required to train the algorithm well. So really, if you want to make your model better, just give it more data.
Okay.
And you reduce the curse dimension. This is a very complicated model. And then we can also see here it's kind of predicted where these mountains are. So this is a rat, I believe, Microzymes.
I think so.
Yeah.
I mean, the one on the left, I don't know the three-toed sloth.
Three-toed sloth, yeah.
Well, I like sloths.
So this was like, is this an example, or are you recreated this like from scratch? Like this was not.
Yes, this graph, this plot was just generated by the computer from an example data set of these dots and these environmental variables, and that's the time that it took for it to compute and generate these graphs.
Did you find the data yourself, or like?
No, this
Okay.
program and this data is part of a collection of examples from scikit-learn, SCIKIT-learn,
Okay.
And yeah, so that's
Okay.
where that comes
Gotcha.
from.
Okay.
Yeah.
I was like really impressed. Like, man, you're like looking for sloths.
This is crazy.
People
Let's see another one.
They're like real time. You know?
It's digits. Plot digits cost.
Hey, Victoria, try pressing tab once you start that. See if it works. Okay, never mind. A lot of times that'll autocomplete if you do that.
Oh, really?
Yeah, you don't misspell.
Oh, that's cool. Okay, so this is another little script from the examples. And this is the optical character recognition that Ron was talking about earlier. This is MNIST, another famous data set. So we can see I don't know if y'all can read these, but what's happening here is that the computer is reading each square, each voxel. It's giving a value to it. And it's comparing not just the value of this voxel, but the value of the voxels all around it. The pixel?
Voxels are 3D. Pixels are 2D.
Pixel. And like he said, feeding a lot of information of handwritten digits in to predict these. So what do y'all think this one is?
C. Or zero.
What about this one?
1, 2, 3.
We're cheating now.
Honestly, I thought it was
Yeah, 4.
It's gonna be
What
4.
about this one?
That's
It's
an
gonna
8.
be 8.
Oh, it could be a 6. I'm not certain. I would say it's an 8 though because of the inflection of the curve. It could either be a delta or an 8, but not a 6 because of the ridge on the left.
What about this one?
Definitely an
8.
8. Well, I can see that it says prediction 8,
Yeah.
but it looks more like
Yeah.
a 9.
But it might be bad. We might have to correct the machine.
Yeah, so I'm not sure if these predictions are actually correct. We can see how there's a bit of ambiguity from the human side.
Mm-hmm.
And so, yeah, I'm trying to figure out. I think that's a 9.
We think that's a smudge with the bice.
Yeah. So we might need to add in some. So what you could do from here is, if you saw that these were both incorrect, is that from this step, if we've already gotten about as accurate as we can in choosing a model, we could begin to fine tune, because sometimes humans will be very good at finding details and noticing things like a smudge. That's some contextual awareness that we might not have been able to feed into the program with data, that we might have to go in manually and adjust a little bit.
Could you do it back up? Like,
Yeah.
sometimes getting it blown up like that really messes.
Yeah, like when you zoom out, you can actually, like that 9 right there, I would actually say it's a G now.
Yeah.
That 8 on the left looks like a 9 to me, though.
Yeah, that's a little bit.
The second one looks like a key.
Your 1, 3, and 4 looks fine. The other ones aren't.
Confusion matrix.
The 9 is really.
Don't question the code. Don't question the code. That's a good. That's a good premise.
Don't question the code.
So I'm going to show you all one more. This one is also image processing. What it's going to try to do is to take a picture of a raccoon and try to find the different parts of its face. And so, yeah, it did a pretty good job. So here again, we're not just looking at the value, we're comparing it to the values around it, because it's able to find these divides and these cuts. Image processing is probably the area where it's easy to see how it would be very easy for a human to do this, but it's actually pretty intensive for a computer to be able to do this. But surprisingly, this is a very basic algorithm, and my little computer is able to run it in 4 seconds. So some machine learning tasks like this can be pretty robust, but generally the applications that get people very excited are often more deep learning applications. The main difference would be the amount of data involved. You need to have more powerful computers and more robust algorithms to be able to handle it. One common architecture would be neural networks. Has anyone heard of a neural network? It's kind of a buzzword, yeah. Neural network. So what's a neural network, Angel?
It's something that has to do with, I don't know, bioengineering, I would think.
Yeah.
It works by testing and counter-testing against whatever samples it has, and it actually strengthens links between each thing it does. So if you've got two things are the same, it strengthens a node, kind of like the TensorFlow does.
Yeah.
So the more something comes true, the higher the value is for the strength of that connection.
Yeah. So this is
Model after the human brain.
a lot how the human brain is thought to work. So the human brain is thought to work, is thought to be able to learn by strengthening or weakening the connections between different neurons. And that changes the way that electricity or ion gradients would, the way the electricity would flow through your brain and therefore change the way that the signal is processed. That sounds a little abstract, and we're going to kind of talk through neural networks a little bit more because we don't want to overwhelm you with the math and statistics. You don't have to understand the math and statistics to be able to get started with machine learning, but to really become proficient, eventually you need to know the math underneath, the math on the back end, to be able to choose an effective algorithm. And so Charles is going to explain a little bit more about neural networks, and we're going to give you a little visual on them.
Right.
The website from.
Okay, so here we have a website. It's called playground.tensorflow.org. And what this website is, it demonstrates what a neural network does. And what a neural network does is it basically takes in data and it tries to create something from that data. Here within the program, you'll see on the top left-hand corner, there's a play button. And if you click the play button, you'll see both a test loss and a training loss. Now, when neural networks handle data, they're measuring the performance of a data set. So the test loss will happen to be associated with the data that is non-compatible, and the training loss is the data that is inefficient to be able to be computed. Here we see some data and data sets. So if you hover over the data on the top left-hand corner, you'll see there are different data sets that you can actually use. One of the data sets being circle.
So what's the task it's trying to do here? If we go to another data set.
So the task it's trying to do is it's trying to formulate or match the data set that is working on. So here it's trying to create the form of a circle, as you can see, a circle. And the exclusive OR data set. So the exclusive OR data set tries to separate the items.
So it's trying to learn how to make shapes and categorize things.
Right, it's trying to categorize shapes. And there's also, I believe, one that's Gaussian. So you can see the Gaussian distribution curve.
Did it flow into and out of? Is that representing flow into and out of?
Oh, yeah, so it's flowing,
Or
the data is flowing through the neurons.
yeah.
So it's flowing through the neurons and it's trying to communicate with the other neurons. And it says the outputs have mixed and varying weights, shown by the thickness of the lines here. Spiral data set.
That one's harder.
Yeah.
What happens if we add some more features in? Does it work better? Or?
Well, if you add some more features, it changed the algorithm.
Mm-hmm.
Yeah, I don't know if we can learn that one.
It's ticking.
Yeah. So like it is developing. It's just it takes different time to develop.
So like, what are some like real world applications for this kind of neural like network? Like, what would be some things like you could actually use this in?
So you can use this for basic classification. If you see in the top right-hand corner, it says the problem type. It's classification. So if you have a bunch of data that you want to try to classify, whether it be something like, animals, you're trying to classify animals that you can find, or you're trying to classify Spam emails, yes, also.
Yeah, that's bad.
And
Let's use that way a lot.
yeah, so like classification is like one of the techniques, and if you click on the classification tab, there's also regression. Regression is another technique that neural networks and machine learning can do.
This would be a much more powerful predictive model, and this would be more like what's used in self-driving cars and a lot of image processing intensive applications.
Yes.
Kind of one of the problems, like what Ron said earlier, how he doesn't like self-driving cars, is because one of the big problems with self-driving cars is like this happens and this, like, it's able to find the proper weights to produce the right outputs. This neural network is trained, these relationships are developed. But let's say that this self-driving car then makes a decision based on this biased network, but let's say its decision for some reason was to run over a pedestrian, and you as the programmer, as the engineer, want to find out what happened. Good luck trying to figure out why it made that decision. Because the whole reason that we use this is because the decision-making process is too complicated for us to explicitly program it, and we can't really read why it made that decision. So that's one of the downsides of making such a smart system.
Oh, black box. Black box.
Black box.
Put stuff into it,
Ideally.
and no one literally knows what's going on inside it.
Right.
There's demons in there.
The old saying that mathematicians sold their souls to the devil is coming alive again is what you're telling me, Ron.
They say the devil's in the detail.
Yeah. And if you scroll down on the page, you'll find out the definition of a neural network. It's a technique for computer program that learns from data. And this is built by Michael Nielsen, or I mean not Michael Nielsen, but it requires understanding of Michael Nielsen's neural networks. That's a good place to start.
And we'll send out this link with the
Right, correct. And you can also repurpose it. This code is source free and it's available on GitHub under the Apache license. So if you have any like other things you want to classify or use linear regression on, then you can try to adapt this code to it. Any questions?
What were they? It was measuring electrons, or what
So
were the individual dots on that neural network?
So the individual dots are basically, it's trying to assign the images. At first in the classification part, those dots specify the location of like where the pixels are in the images. So it's just trying to repurpose the images into a easy to see collection of dots in a representation. And
is it representative? The flow is the representative of neurotransmitters? Or?
Data.
this is data, yeah.
Yeah, but yes, if you wanted to equate it to an organic system, it would be a higher concentration of the neurotransmitter.
Okay.
So the weights would be that you would give more emphasis to the output from a certain node into the next layer, and so that that node has more impact. And yeah, so it would be basically math in between the neurons, if that's what you're asking. Like, what is that line? Some math.
It's math.
Okay, and now we give it to Lynn to talk about the club specifics. Yes.
Hello everyone, my name is Lynn. I am a new member officer, so I'm so happy to see a lot of new faces today, and I also welcome returning members. Hopefully we're gonna have a really good learning experiment through machine learning this semester. I am here to help a new member especially. If you have any question, concern, just let me know. You can either meet me after this meeting or email it to me. I try my best to answer your question because last semester we already started some meeting where we help people to install Python on their computer. And we also run some symbol coding, and we also pass out some Python cheat sheet that may help you out while you're coding. If you need any of this, just please let us know. Let's see. Right now, we have some project that we are currently working on right now. The first one is well logging of Dr. Robinson, our electrical professor. He gave us the data set that we can play around with it. So if you want it, just contact with any of our officer right here. So we would give you a chance to practice on it. And the second project that we're working on right now is, that is the meeting with Dr. Wen last semester. He came one day and showed us what he's working on. He's working on the speak recognition research, and then this is also a really good resources that you can practice on. Third project that we are considering right now is we are helping a group of mechanical senior students. They has composing analyzer, and that's analyzer collecting a lot of data, and they need some people to help them organize it, analyze it. So if you're really interesting, please let us know so we somehow find a connection so you can practice it on these data. And lastly, this is really like brand new project that we just basically start. This is gonna be a lot of challenging. If you're interested to join us, it is called Drone Case. Basically, we try to design a case that have propeller and motor system that can help your phone flying around. So you can use now selfie or video theater, movie mode theater with hand free. So it's gonna be really challenging. So if you're interested with any of this, just please let us know. So any help can be worth it. Yeah. This club basically a self-learning environment. So we try to encourage everybody. If you have any idea, project, or anything that you want to show us, just please contact with email to us, contact any officer here, so we can give you a chance to like promote to people. So basically, this is all about HECML. You know our staff, our officer, how we function. So now we want to know more about you. So right now, Nate's gonna hand out a survey that you can use your phone scan and answer some question on it. And yeah, any idea, project, please let us know.
Yeah, so this, like Lynn said, this is survey, just to get some feedback from you guys on a little bit, get a little bit more knowledge about who you are and where you might want to contribute.
No, they have a sign in.
Yeah, this is a sign in.
That's the sign in. This is survey is different.
This is the survey one.
They have a sign in.
Oh, they have it.
Yes. So
Oh, yeah,
everyone
yeah,
is
yeah.
given.
So this is different from the sign. Also, just an announcement, we're gonna have a bake sale. Bake sale on Valentine's Day, so be on the lookout. Bring
sale.
people to our today, so we can start raising money for more products. But I don't know if there's anything else that anybody else wants to add.
One more announcement. So next, our plan is to meet every week at this time. If you have some friends that are not available to come at this time, but you might be interested in working with us or learning with us, we will have these lectures available, videotaped, and we will, our website is not up yet, but we are more than happy to work with someone that can't come at this time. Next week, we will have an interactive coding session with Dr. Robinson. So basically, he's just going to sit over here and show us some Python basics, show us some machine learning basics, and so you can bring your questions, and you can ask him questions, and he'll kind of answer it with code. If you are sort of a newbie to programming and you're nervous about installing Python or you have any questions, you're always welcome to stay after the meeting and we will help you out.
Yeah, go ahead.
Python runs on Mac, right? Runs an application. Because I know Linux is like.
We are suggesting Python 3.6. So we can all be on the same page and get the same code out. Yeah, 3.
whatever's on their website right now.
3.6, yeah.
Do you guys post like links for this?
I know they're headed for 3.76. I don't know what
You guys were gonna post links for this?
Yeah. And so we all have your email, so be on the lookout for any emails or coordinating from me or one of the staff, and we'll send out those links and stuff as long as you sign it and give us the email.
When is he signing?
Yeah.
Any other questions?
Any questions? Any comments, concerns? You can also suggest anything that you that maybe you have an idea for a project or maybe something that stuck out to you on this survey. But that'll be it, I guess. We'll conclude. Good luck in classes.